So what was happening to Florida all this time when it was underwater? Isolated from North America by the Sewanee Straits, Florida became a carbonate factory, an environment conducive to the accumulation of vast thicknesses of limestone and dolomite. A modern analog of a carbonate platform is the Bahamas, which are made almost entirely of carbonate rocks. Like the Bahamas, the Florida Carbonate Bank thrived because it was isolated from the main continent by deep waters. Remember, carbonates are rocks made of calcite, aragonite, or dolomite and are precipitated sedimentary rocks. Almost all of them form biogenically. Organisms make shells and other hard parts out of carbonate minerals, and when the animals die, their hard parts accumulate and become lithified into rock. The organisms that make carbonate minerals can live both attached to the seafloor and in the water column. Carbonates that form attached to the bottom are principally corals. The corals need sunlight to survive and so grow upward to remain in sunlit waters. Carbonates that grow in the water column are principally photosynthetic plankton, like these microscopic coccolithophores shown here. When they die, they collect onto the bottom of the sea and become lithified into limestone. Both kinds of carbonates form on a carbonate platform like the Bahamas or Florida, giving a rich variety of rock types. Here's a cross-section across a typical carbonate platform showing the reef rocks along their edges and water column carbonates collecting inside and outside. In the middle of the lagoon, water is very sluggish, and the typical sediment that accumulates here is a carbonate mud that sort of looks like this. This kind of sediment is very common in the still water lagoons around the Florida Keys and Florida Bay. So what are the requirements for a carbonate bank? First, the water needs to be shallow, especially for the formation of reefs. The water needs to be warm and tropical. And most importantly, there needs to be no contamination with terrigenous or land-derived sediment, and the bottom has to continuously drop out to provide accommodation space. Let's look at the last two requirements in more detail. Carbonate-producing organisms cannot tolerate terrigenous input for a couple of reasons. One, it makes the water turbid, which reduces the ability of sunlight to penetrate, making it difficult for reefs to survive. Second, the sediment harms the polyps of the reefs, eventually killing them. So in order to thrive, especially for millions of years, a carbonate platform must be protected against any influx of terrigenous sediment. The Florida carbonate platform was protected against the influx of terrigenous sediment by the Sewanee Straits. This deep trough swallowed up sediment shed off of North America and prevented it from reaching the shallow carbonate platform to the south. This is how it worked. Sediment eroded off of North America, was carried by rivers into the sea, and started to move south. But once it fell into the Sewanee Straits, it was captured and couldn't move farther south. The Florida Carbonate Bank was protected. And it's important to remember that for millions of years, a huge amount of sediment was being eroded off of North America. The Appalachians, which are shown here in red, were a high and rugged mountain range like the Himalayas initially and more like the Rockies later on. Rivers draining these tall mountains carried vast amounts of sediment, and much of that sediment destined for locations to the south ended up in the Sewanee Straits. Now let's turn to the last requirement for a carbonate bank, subsidence. Subsidence is necessary because carbonate banks are formed over shallow water, and if you want to accumulate more than a few meters of sediment, the bottom has to keep dropping out to make more space. Here's an animation of how it works. The water has to stay shallow so that carbonates can form, and the floor keeps sinking to allow more and more carbonates to accumulate. On the Florida platform, over 4 kilometers of carbonates have accumulated, all of it in less than about 10 meters of water. So what causes the subsidence? Subsidence is common along passive margins, leading to thick accumulations of sediment for a couple of reasons. One is that the floor can move downward along normal faults. Remember, normal faults always form as the result of rifting, and continued movement on these normal faults allows the area to subside. The second reason is due to contraction due to cooling. Recall that rifting involves the intrusion of magma, eventually leading to the formation of a mid-ocean ridge with continuous volcanism. Rifted margins are always full of magmatic intrusions which heat them up, and as these anomalously hot regions cool, they contract and sink. Both of these features are present deep underneath Florida, and the continuous subsidence they caused allowed for an enormous pile of carbonate rocks to form on the Florida carbonate platform. I know you can't read the labels on this cross-section, but they all correspond to the names of carbonate rock formations. Florida is largely built upon a foundation of a great thickness and great variety of carbonate rocks. Much of the variety is due to changing sea level during this time. Although the great majority of rocks that formed from 150 million years ago to about 15 million years ago were carbonate rocks, there are also some evaporate rocks intercalated that formed during sea level low stands when seawater became trapped on the platform. The super salty water also sank through the existing carbonate rocks and converted some of them to dolostones. Remember, dolostone is a rock made of dolomite, which is made when limestone reacts with magnesium-rich waters, and half of the calcium in calcite or aragonite is replaced with magnesium. The end product of all this carbonate deposition, coupled with rising and falling seas and the formation of dolomite, is a thick pile of an incredible variety of carbonates. We now have to continue our story, which you may recall was paused at about 15 million years ago. The carbonate factory had been going great guns up to this point, but it was about to abruptly end. The end happened when the Suwannee Straits, which had been swallowing up sediment shed off the Appalachians for 150 million years, finally filled up. With the Suwannee Straits no longer blocking the transport of sediment southward, the carbonate platform was soon buried under terrigenous sediment, first fine-grained clays and silts, and eventually coarser sands. Here you can see the last vestige of the Great Florida Carbonate Platform, with a tongue of land starting to extend across the Suwannee Straits. By 8 million years ago, the straits are full and land is starting to migrate southward over the Florida Peninsula. 3 million years ago, and 1 million years ago, during the height of an ice age, where you can see the great ice sheet extending over much of North America. So let's try to simplify and summarize. If we were to draw a cross-section across Florida, we'd see a stack of sedimentary rocks overlying igneous metamorphic basement rocks. This is what it would look like. We have the igneous metamorphic basement rock overlain by a thin layer of terrigenous clastics, then a vast pile of diverse carbonate rocks, and finally a thin layer of sediments on top. Note that this cross-section is only schematic and that the thicknesses aren't to scale. By far, the thickest layer is the carbonate rock layer. Each of these layers tells a story. The basement rock is a remnant of Africa left behind when Africa separated from North America. The sandstones and shales formed in the opening rift basin, with clasts eroded from the adjacent continents. The carbonate rocks accumulated and were modified on the Great Florida Carbonate Platform, and the sediments were deposited on top of all of them after the Suwannee Straits filled up. We've omitted one final aspect of Florida geology, and it's an important one. The limestone beneath Florida has been variously eaten away by weathering, leading to a kind of rock called karst. You can see what karst looks like at the rare locations where rocks are exposed at the surface in Florida. Here we can see a limestone that's been furrowed and pitted along perpendicular planes. The planes were originally cracks in the rock, we call those joints, but have been enlarged by the action of weathering. Here's another exposure of karst. The surface here is more irregular and the depressions are full of soil and vegetation, but the actual relief on this surface might be as much as 5 to 10 meters. Karst is produced when carbonate rock, especially limestone, is attacked by acidic surface waters. The water becomes naturally acidic by dissolving a small amount of CO2 gas, producing a weak solution of carbonic acid. The weak carbonic acid dissolves the calcium carbonate. Water penetrates the rock along fractures and enlarges them, or follows the fractures into the interior of the rock, producing cavities, pits, and even caves. Most karst-producing dissolution occurs at or above the water table, the surface that separates saturated groundwater below from the soil zone above, where air is also present in the pores of the rock. You might think this would lead to a relatively narrow zone of karst. However, the water table moves up and down through time and driven in part by changes in sea level. As the water table moves up and down, the zone of dissolution sweeps through the rock, converting large regions of limestone and dolomite into karst. Karst-forming processes have operated in Florida for a long time, including times in the distant past when sea level was lower and rock was exposed, even on the carbonate platform. As a result, almost all of the carbonate rocks beneath Florida, shown again here in this cross-section, have been karstified to some extent. This karstification has dissolved away many tons of rock and also may explain why the rocks are gently arched upward. The main arch seen in the cross-section across peninsular Florida is called the Ocala Arch. Remember, because of the vertical exaggeration, the rocks are in reality only very slightly bent upwards. Some geologists think that the force responsible for the Ocala Arch is related to karstification. The key idea here is called isostasy. Remember, the lithosphere is rigid and the asthenosphere acts like a fluid. This means that the lithosphere in some sense floats in the asthenosphere and can adjust its position as its weight changes. Adding weight to the top, like the weight of a huge glacier, will depress the lithosphere into the asthenosphere as it sinks a little lower. The asthenosphere will flow out of the way to accommodate the sinking. When the weight is removed, the lithosphere will rebound upwards, once again being facilitated by flow in the asthenosphere. Because flow in the asthenosphere is slow, because the asthenosphere is so viscous, isostatic rebound doesn't happen quickly, but occurs slowly over tens of thousands of years. And in fact, we can still observe it happening today in places like Scandinavia and Canada, as the lithosphere slowly responds to unloading caused by the melting of the ice sheets that last covered them about 18,000 years ago. But isostatic uplift doesn't only happen when glaciers melt, it can also happen whenever any load is removed from the surface of the lithosphere. It happens due to erosion, for example, as shown in this diagram. As material is eroded off the top of the lithosphere, its weight is reduced and it responds by bobbing upward. It stands to reason then that isostatic uplift can also occur when material is removed by dissolution. In fact, calculations show that so much material has been dissolved out of the carbonate rocks under Florida that Florida should have been bobbing upward at the rate of about 10 to 15 meters every million years. This is indeed what is inferred from some odd locations of marine terraces that are presently found high above sea level near the center of the state and apparently have been lifted to that position by isostatic uplift.